can watch the movie later on. So, how I see, accept them all. So. So 7 minutes after, let's start with a short introduction from my side. So hello and welcome everybody to this first open software-defined Vehicle of the Future initiative community tech talk organized by Federate. So I'm Mario Triussi from the Virtual Vehicle Research Center in Graz, Austria, and I will moderate this. So it's really great that there are so many people interested in this software-defined Vehicle of the Future initiative and also in this hypervisor topic about XEN. So maybe some words about this new series. So on the one hand side, we want to present in this open series where everyone can participate, not only Federate and Hard for SDV members. So someone is laughing. Building blocks which can be used and which are ready to be used in this software-defined vehicle reference architecture. And on the other hand side, we want to organize some discussion rounds where we can discuss about topics like what makes a free, libre, and open source project interesting for OEMs so that it leads to commercially, let's say, successful utilization and project participation. So you see there are quite few topics we plan to discuss and to present. But today, let's say we start at the bottom at this SDV reference architecture. So if we talk about this reference architecture, it's always the same, let's say, for these architectures. We're talking about the hardware platform, some low-level drivers, build support packages, firmware, then you have an operating system. And on top, you have some middleware and applications. So in this reference architecture, there is everything between this application and the hardware. So, and for that, today we want to start at the bottom of this software-defined reference architecture, where we have some kind of abstraction of physically IT resources, let's say, where we can use a hypervisor to virtualize our operating system and run several in parallel of them. And for that, I'm very pleased that we have Stefano here. Stefano Stabellini, hopefully pronounced correct, is from AMD, and he is one of the main drivers of this XEN project, which is a Linux Foundation project. And he will give us a talk today about the XEN hypervisor for automotive, real-time, and safety. So really great to have you here, Stefano. So only 2 more sentences from my side so that everyone is aware. The video or this tech talk will be recorded and published. So I will forward the recording to the Federate Dissemination and Communication team, and they will provide access to it via the Federate web page or to this Federate YouTube channel. And second thing, if you have any questions, so please write them down, make a note, and ask after the presentation. So then I will stop sharing and hand over to you, Stefano. Stage is yours.
Well, thank you, Mario. It's great to be here. Thank you for the opportunity. Let me share the screen and I'll start from there. You see my slide?
Yes.
All right. I am a fellow at AMD. I'm Italian, European, although I live in California nowadays. And so what is XEN? So XEN is an open source project under the Linux Foundation. It's very well known in the industry and widely used across multiple verticals. And it's also famous for a very strong review process and security process. By review process, I mean it's famously difficult to get patches into XEN because the review is extremely strict. And security process also as one of the best, if not the best, security process for handling security vulnerability in the open source industry, which is these are 2 of the reasons why XEN is actually a great foundation for any project where safety or being critical, handling critical tasks is important. ARM and x86 are both supported today, and RISC-V is in progress. There is an effort in the industry to continue the RISC-V development by including Resiltech, which I believe is attending this meeting. Another key element of the XEN project community is that it's a diverse multi-vendor community, a bit like Linux, in the sense that it's not dominated by a single vendor. There is a multiple vendors and maintainers from multiple companies across the board. And you can see a pie chart of contribution for 420, which is about to be released. So it's not even quite finished yet. It's one of the last RCs, but just to give you an indicative idea. And I'm very proud to say that AMD is a second contributor in this release. But one thing that is interesting for people that work in automotive like us is that Honda joined XEN project in December 2024, as a paying member. In addition to that, Ford has been joined the XEN development community in the sense that started sending quite a few patches and reviewing code and interacting on XEN project for hypervisor development. This is very recent as well, like from the beginning of this year. Okay, what is then? How does it look like? So the architecture is very much aligned. What you see on the picture is the ARM version, as a reference, but I could say it's the same thing for RISC-V. And x86 is also very much aligned, and we'll cover it in a second. So I'm going back. So XEN runs entirely and only in hypervisor mode. So it runs at EL2 and only at EL2. So it has control over a few of the key elements of the SoC, such as the timer, the interrupt controller, the MMU, the IO MMU, the PCI root complex, of course, the CPU to do scheduling, but that's it, nothing else. So what we usually call devices, such as, SATA controller, MMC controller, Ethernet controllers, GPIOs, anything else really is not controlled by XEN. XEN doesn't do anything with this. XEN just assign them to a domain, and the domain can just use them. They can be either assigned to DOM0, which is the default, is the first domain to start. That would be the default place where all of these devices go. But they can also be assigned to other VMs. Like in this picture, there is an example of a SATA controller being assigned to a DOMU. Not only that, but these devices can be shared. And we'll talk about sharing more later, but the way it works is there is a front-end and back-end architecture. The back-end is basically like, the back-end is this element here running in DOM0 in this example, and it's basically like a proxy. So what is doing is proxy requests from front ends, there can be multiple ones, and mediating them over to the real driver for the device. And there is one for each class of devices. So there is a backend for audio, for network, for disk, and so on. We support two classes, I would say two technologies of these front-end and back-end connections. One is the XEN PV drivers, which is XEN specific, but also the VertIO technology, which is hypervisor neutral, and they're both pros and cons, and I'll cover a little bit more later. So the x86 architecture compared to ARM RISC-V is older, there is more legacy, but I'm pleased to say that with recent development is also fully aligned with the before, with what I just described. XEN runs entirely and only in host mode, and the VMs are as small as possible while still using hypervisor extension. This is what I mean by there is no need for any emulation, it's only PVH. We got rid of all the legacy here that was present, and there was a lot of emulated devices that needed to be there, like Southbridge emulation, floppy disk even, CD-ROM is all gone, and now the architecture matches pretty much what we just described for ARM and RISC-V. So all the three major architectures are aligned. So I think the key message here, and I'm going to try to cover all the key details, is that XEN can run from simple system and my example for Vision Hub, for the simple system is Vision Hub. And people that work on the Vision Hub, I'm sure they will be laughing right now because it's anything but simple. But I'm saying simple in the sense of hypervisor configuration. Typically, the hypervisor configuration for the for sensor processing is simple because it's all about real-time and static partitioning. So it's lower complexity from a hypervisor perspective. On the other end, at the opposite end of the scale, you have systems such as IVI, which are very complex from a hypervisor perspective because there's a lot of device sharing. So you share input, audio, touch, obviously the screen and more. So XEN can go from the one end of the scale to the other end of the scale. And I'll cover the key feature to do both. In some systems, AMD system, as an example, you can have an AMD x86 system doing the IVI as an example on the left, maybe, a Cortex-A based system on the right to do the Vision Hub, and they can be connected over PCI, and both of them could be running XEN on the same vehicle. This is actually an architecture that we are productizing, and you can see demos if you're going to be at Embedded World of this architecture. In later slide, I had some even more interesting details to share about this. Okay, let me start from details of the simple case first, right? So first of all, XEN can do scheduling of virtual CPUs over physical CPUs. So these green boxes are the physical CPUs, and I'm showing how they could either be scheduled, meaning multiple virtual CPUs over a single physical core, or they could also be fully dedicated. Now, of course, for static partitioning, simple system where real time is essential, you want to do no scheduling. Statically dedicate the physical core to the virtual machine. And that's what we do with the null scheduler. As the name implies, there is no scheduling being done. It's just a way to disable the scheduler. So for static partitioning, that's what you would want to do, and that is the best for latency and real time. Another key feature for static partitioning, but honestly, we are using this even in IVI, is DOM zeroless. Sometimes it's also called hyper launch. It's the same feature. So in old XEN system, what will happen is XEN starts DOM zero first. It used to typically be a large Linux system, and then this DOM zero system will have the tools to start additional VMs. So you start DOM zero, and then DOM zero as a tool called XL to create other VMs. Now, that is not great in embedded, automotive included, for a number of reasons. But one of them is boot time. Another one is that DOM zero becomes very critical in the boot flow and is also highly privileged, meaning that DOM zero can start and stop VMs, can reboot entire systems. It becomes a problem from a safety perspective. So what we did is we got rid of DOM zero. To cut the story short, we didn't entirely remove DOM zero, but we made it optional. So the way now it works, XEN starts all the VMs in parallel at boot, including the yellow VM, the purple VM. So if you have an RTOS as one of the VM, it could start in far less than a second without doing any special configuration. So you have great boot time, improvements, but the key benefit is not even the boot time. Is that because DOM zero is not required to boot the other VMs, you can actually not have a DOM zero. So DOM zero become optional, so you don't need to necessarily safety certify the DOM zero environment. So in summary, how does it look the simple case? Like in the sense of everything is statically assigned, we are just splitting the SoC into 2 or more domains. There is real time. Basically, XEN is as small as possible. Try just to get out of the way. So you configure the system using DOM zeroless. Everything is configured statically. So memory, number of virtual CPUs, devices where they go, either one domain or the other. No scheduling. DOM zero is optional. You can have it or not having. not having it. No hypercall means the domains, they don't even have to know XEN is running. You can have a completely non-XEN aware system without any problems. The footprint at runtime is minimal because then is only looking for, handling these timer, UART, interrupt controller devices we just discussed. IOMMU, okay, this is an interesting topic. So normally XEN will protect device DMA using the IOMMU, but it's possible to have protection in place without the IOMMU as well, and I'm going to cover it in a second. And I also wanted to mention that XEN can even run, if I didn't convince you XEN is an embedded hypervisor, that should convince you XEN can run on Cortex R52 and Cortex R82. These are systems without an MMU. So these are MPU-based systems. There is no memory translation. So everything is really static and based on address ranges. And so XEN can run on R52 and R82 as well. So let me explain why the IOMMU is optional rather than mandatory. It's because XEN has a feature where you can allocate all the memory of the guest as one-to-one. So normally, as you see, the guest see memory in terms of guest physical addresses that are not the same as physical addresses. So normally when a guest programs a device, the device starts a DMA based on guest physical addresses that needs to be translated by the IOMMU in order to reach the right physical address as in DDR. So because XEN can map memory one-to-one, meaning guest physical equal physical, then the device can start the DMA using the physical address directly. Now you don't need an IOMMU to translate it any longer because guest physical equal physical. So you can get rid of the IOMMU completely and just rely on the what is called in terms of AMD Xilinx devices, XMPU. Other vendors has other names. Point is, these are bus filters. They're much faster and lightweight. So you can still have protection even without the IOMMU with XEN and one-to-one memory allocations. I also want to cover the last of the feature for this, more on the embedded and real-time side of the scale, which is cache coloring. So often it's the case that on many SoCs, there is a shared L2 cache across multiple cores. And the problem with a shared L2 cache is that it can be a vehicle for interference, meaning that because there is a significant time difference in accessing memory, if the L2 is in contentions or not, you can get very high variability in terms of performance and latency. This is undesirable. So XEN has a technology called cache coloring that allows you to split the L2 cache in software, splitting the cache line into different groups and basically using different cache line sets in different VMs. And these ways, there is no interference. I'm not going to go into the details because it's actually a very interesting and non-trivial technology. The allocation, I'll cut the story short. You need to allocate a page in memory every 16 pages to avoid interference and making sure each VM get a different set of cache lines without any shared cache lines. But I can tell you the results that are really outstanding. These are you might have seen in the past. This is not new results here, but they've been out for a couple of years. So just want you to look at the high rectangles, the ones that are above 10,000. I think this is nanoseconds. These are this is the latency when you start adding interference. So you start adding interference, you see the latency really jumps up, while this low number below, the one you see my mouse arrow, the one that stay down below, this is the same measurement, but with cache coloring enabled. So I think the takeaway of this slide is with cache coloring disabled, cache interference causes your latency to jump up, while in the same situation with cache coloring enabled, the latency stays pretty much unchanged. Now let me go to the opposite end of the scale. Many of you might be working on IVI and more infotainment systems, larger systems, and larger systems are more complex at least in terms of hypervisor configuration. And in this example, this is an example of an AMD-based IVI system, and that we productized. And you see on the right how many VertIO and PV driver we have. We have PV audio, VertIO net, block, GPIO, T, I2C, and input. All of these are front end and back ends to share, to share network, to share the disk, to share the screen, to share input, to share audio, and so on. So it becomes quite a complex configuration, and we can handle it. So XEN does support both PV driver and VertIO. You can pick the best for your solution, and we typically use QEMU for to provide VertIO backends, and we vastly improved the way QEMU provides these VertIO backends. So we created a very, very small QEMU machine. What a QEMU machine is, for the people that are not used to working with QEMU, it used to mean the thing QEMU is emulating. Nowadays, it doesn't really mean anything specific. I mean, QEMU machine really mean the set of hardware that you are emulating in QEMU. So we created a machine that is only for VertIO and exclusively for VertIO, and it works across architecture. So it works on x86, it works for ARM, it could work on RISC-V without any issues, and is much faster than before, much more lightweight. So we are making improvement to the open source VertIO backends implementations. And all of these can be started with DOM zeroless. So there is no problem. So you can have a parallel start and also use PV drivers and VertIO. There is a way to synchronize as soon as the backend become available, the front end connects to it automatically. So we have already solved that problem for both VertIO and PV drivers. You can have those and the parallel boot without issues. I want to also mention quickly one thing. So the VertIO GPU is, while my team specifically enable most of the XEN-based technologies that you saw in this slide, VertIO GPU has been done in collaboration with the GPU driver team at AMD and does fantastic performance. It's a purely software solution to get above 90% of the native GPU performance, and it's going upstream in QEMU. There is development right now to upstream the VertIO GPU backend. So it's a purely open source solution. All right, so let me touch on safety. So safety is such an important topic for, I think, many of us here in automotive. So AMD is working on making XEN safety certifiable, IC 61508 Seal 3, and also ISO 26262 ASIL D. Which is the strictest level for automotive, and we're targeting ARM and AMD x86. But what I want to highlight here is because many open source projects, including XEN, have been safety certified in the past. The way it was done in the past is someone will fork the project, internalize it into the company, and then basically make it their own. So they would make changes to the source code, changes to the contribution process, changes to everything, and then reach the certification. So this is not at all what we are doing. So we are, all the safety certification artifacts and documentation are based on upstream code, upstream processes, such as upstream review process, upstream contribution process, upstream security process. So upstream everything. And we are planning to, and we already are, and I'll share some example later here. We are not just making public, but even upstreaming to XEN many of these safety certification artifacts, including all the code changes, MISRA-C changes, as well as the requirement, the architecture specification, and more. Okay, let me talk to you about the safety concept. So what is the architecture for safety? So we implied DOM zeroless. So DOM zeroless to start multiple VMs in parallel. You might remember in the previous slide, I had a single domain called DOM zero here. So DOM zero was too much, too powerful, having all the drivers and also being able to destroy VMs, reboot the SoC. It's too much for a single VM. So we split DOM zero into two. Now we have the hardware domain and the control domain. The hardware domain has all the hardware by default. So it will typically have all the device drivers as well as the backends, you know, the Virtio or PV driver backends, but is not privileged. And by that, I mean, it cannot destroy another VM. It cannot cause interference to a safe VM, right? So the hardware domain is restricted in a way it can do his operation is like a normal domain. So it cannot cause, it's free from interference from safe VM. Safe VM are free from interference from it. So there is interference isolation with the hardware domain. The control domain, on the other hand, is small, has no hardware, but is privileged. So you can have like a tiny RTOS as control domain that is doing monitoring, destroying VMs, rebooting the entire system, doing highly privileged operation, safety certified, most likely. But the control domain is optional. You don't have to have it. You could set up a system without it. And just for maximum flexibility, this slide is the same as the one before. I'm just trying to explain that you can have more than one hardware domain and you can have more than one safe VM. So it's not like you can have only a single safe VM that is a control domain. You can have multiple safe VMs and you can have multiple hardware domains. Like you just assign devices, run the backends, and we'll call it a hardware domain pretty much, right? And they don't need to be necessarily safe, right? In the sense, in terms of interference and privilege level, from a XEN perspective, they don't have to be safe. So in summary, these are the features in scope for our safety effort. There is no hypervisor OS dependency. You can run any OS on XEN, you can run Linux, you can run Zephyr, you can run FreeRTOS, you can run the proprietary one, you can run VxWorks, anything. All the key drivers for the key component the XEN is controlling, the one I mentioned a few times now, the UART, the UMMU, the interrupt controller, the timer, the PCI complex, those are in scope. Static configuration, so everything is statically configured. So the number of domains, the memory, the scheduling or no scheduling. There is no dynamic memory management in the sense that you cannot allocate new memory to domains, so deallocate new memory from domain. We're actually working closely with Minerva to look in detail at the memory allocations that happen at runtime to be fully under control. So domain can be individually rebooted by causing minimal disruption. That's not really, it's more like a reset. We can reset a domain to the initial state. So all the memory allocation stays in place. There is no disruption. Device assignment, PCI and non-PCI, of course, is in scope. Like this is the key to be able to, in this example, have the Ethernet driver and controller in the first hardware domain and the NVMe driver and controller in the second domain. Like, so obviously device assignment is in scope. Scheduling, no scheduling is in scope. Control domain and hardware domain separation. With the hardware domain that can be QM. QN, for the one that are not familiar, means non-safe or unsafe, meaning not necessarily safety certified. And now the most interesting question of all, what about VM to VM communication? VM-to-VM communication is a very difficult topic here. And I'm going to try, will deserve a full hour. So maybe in the future, Mario, we can have a comeback on this. But I can spend a few words on just a couple of words to introduce the topic. And so XEN supports, first of all, simple VM-to-VM communication mechanism. And by simple, I mean things like static shared memory and event channels. So you can roll your own protocol over shared memory. Event channels are just like software interrupts. You can do your own protocol. You can also do a little bit more dynamic sharing with the grant table. They're all very simple protocols. You can use Argo, which is like a hypervisor mediated memory copy. That's also very simple, and it looks a bit like a socket. So you can use that. All of these, they will be part of the safety scope. Very easy to implement byte exchange between VMs. They can be between safe and unsafe VM, between two safe VMs, any way you like, because these are very simple systems. We can guarantee they're basically safe. VirtIO and PV driver is a much harder question because they're complicated systems, and the basic building blocks in XEN will be part of the safety scope. So I could stand here now today and tell you truthfully the VirtIO and PV driver from a XEN perspective are safe. And I would be saying the truth. The problem is, in reality, that's not how you're going to be able to deploy these things, because all the existing implementation are not written with safety in mind. The ring protocols are not designed for safety. Even worse, for VirtIO specifically, there are dangerous synchronous operations that cause wait times in the front ends that are not acceptable from a safety perspective. There are dangerous memory mapping operations that again cause interference to the front end. The front end is particularly exposed. While the backend, it might be possible to write a backend today which is safe, but again, there is no, at least among the open source implementation, I think there is no safe implementation of any backend as a reference. So in short, I think our current recommendation would be to use VirtIO between QM VMs. And this is totally okay. Like if you see this picture as an example, you can have the hardware domain as QM, like a normal Linux. You can have DOMU, again, that's using VirtIO here as, again, QM, like Android for infotainment. And then you can have on the side one control domain based on Zephyr or FreeRTOS or TinyRTOS that does only a very specific task, which is safety critical, like Telltales or I don't know, anything, something very constrained. And that could still be safety certified, protected, is doing its own thing and is not interfered by the VirtIO mechanisms. So that's doable today. But we also want to make VirtIO and PV driver possible between safe VMs or safe and unsafe. So we are working on two VirtIO protocol extensions that will allow the implementation of safe VirtIO frontends. They are actively in development, and we're working on a POC at the moment. So another important news that I want to share with you is that so our safety project is based on two steps: the safety concept approval first, and the final assessment second. And we achieved the safety concept approval in November 2024. So that is 3 months ago, 4 months ago. So this is a critical achievement. I cannot stress this enough. So for the one of you that are not familiar, so the way this works is you present all of your plans, examples of everything, example of the requirement of the test, of all the planning documents, the verification plans, the architecture spec. You write everything down, you present it to the assessors, and the assessor tell you if you are on the right path or if you have any gaps. And if you are on the right path, they give you a signed approval of your safety concept. And the idea is now is just execution. So of course there is still a lot of things to be done, and we are working full steam ahead on making progress, but the concept has been approved, so I can now really stand here and say the XEN can be certainly safety certified. So what is the status in general in terms of upstreaming? So we are nearing completion of most of the safety relevant code changes, including DOM zeroless and all the static configuration, PCI pass-through that has been re-implemented to work well with DOM zeroless and be safe. So the PCI pass-through code is in XEN now. That is nearing completion. MISRA C compliance, I have a better slide later, but we are really close to the end of that activity. What is instead at the beginning or just still ongoing? So we are still working toward implementing the hardware domain and control domain separation. We are working on upstreaming and making public and also just writing assumptions of use and software safety requirements and the software architecture specification. So we have quite a few examples out there, public and upstream already, and we are going to make public a lot more soon. So what are the software safety requirements? So these are all the functional requirements on your software, the way it needs to behave, all of the behaviors needs to be written down so that they're not just clear, but also testable. I'm going to give you more update on this in a couple of slides. So let me first give you a quick update on MISRA. So the first activity was to identify the MISRA C rules that are relevant to us, and then discuss them one by one with all of the maintainers to get their buy-in and also the buy-in of the community to adopt these rules as part of the XEN coding style. We have done so. We have completed that activity, and we have now 120 rules adopted in XEN project. And Bagsen really helped us a lot here, discussing the rules one by one, explaining it to the XEN maintainers, and also fixing violations. There were 148 commits to fix MISRA violation in XEN 4.18. There were some more in other releases like 4.20. And the current status is we have 87 rules that have 0 violations and 70 more rules that have not many, just a few violations. And they're all checked automatically as part of our CI loop using the Eclair MISRA C scanner against regressions. Software safety requirements. So I mentioned these are the detailed documentation of all the expected software behavior written in plain English. They need to be clear and unambiguous, consistent, and they're divided into 3 levels. The market requirement, that are the higher level requirement, product requirement, a bit more in details and start to be XEN specific. The software safety requirement are really, really in details, individually testable. So we have structured requirement into these layers and also worked on traceability. By traceability, I mean this market requirement need to be linked to the product requirement, which need to be linked to the software safety requirement and then to the test. And all of these needs to be workable in both directions. We have put the system in place upstream to do that, which I'm also going to share in a second. So the first key thing that we really did is for the people, the one of you that worked on safety, typically requirements and traceability are handled with complex and expensive proprietary solutions such as JAMA and others. And they couldn't possibly work in a open source environment where anyone can contribute changes. We cannot create new JAMA accounts for every contributor. We need to come up with something else. So what we did is we use requirements as text document or requirement as code. What do I mean is in recent years in the open source community at large, in GitHub as an example, you see many open source projects are using plain text files either in Markdown or RST format, which are plain text formats in Git for documentation. That's the README you get when you go to any GitHub open source project. And these RST or Markdown files can be converted into PDF and HTML easily. And they use the same contribution model as code and the same versioning control in Git. So we are using that. This is an example of an RST file, a requirement written in RST being converted into HTML. So we are using really, RST, plain RST files to write requirements and keep them in Xen.git, reusing the same processes the open source community is very much familiar with for code review and also for versioning. And we are now we just need the tool for doing the linking for traceability, and we adopted OpenFastTrace among many open source tools that are available, especially StrictDocs is pretty similar. So OpenFastTrace, what it does is simply work based on tags. So it looks at tags in different documents. So these are tags, and based on the presence of these tags, it can create the linking. And each tag can have its own unique version. So there is an additional versioning at this tag level. And this is an example of the traceability report that OpenFastTrace produces, showing where with the green tick when things are okay, where the traceability is all the way through, or when something is broken in the traceability report. I want to conclude with one very cool feature that I don't know if some of you might be interested in, but we are working, and we might have a demo at Embedded World for the one that are attending next month, of a technology to have, when you have Xen running on one SoC and Xen running on the other SoC connected via PCI, so they can be heterogeneous, so an x86 and an ARM system and a RISC-V system, anything that you like. We are going to have Virta.io running across the PCI link. So in this example, we can have the Ethernet connected to one VM on the x86 side, then run the Virta.io backend on the x86 side and the Virta.io frontend across the PCI link, connecting to the backend on the other end of the PCI link and getting access to the Ethernet that way. So you'll be able to use Virta.io across PCI among Xen virtual machines. And this is my conclusion slide. So I'm going to leave some minutes for questions. We are working on making Xen safety certifiable. All the work is based on upstream community processes, upstream code. We are upstreaming code changes and requirements and other things right now. We have bi-weekly meetings on this topic. There are many members of this special interest group for Xen safety. It's free to join, and we have people such as Roberto from Resiltech, Renesas, Francesco from Resiltech, Renesas, Ford, Boeing, EPAM, ARM, Baxeng, and others. So let's work together on making Xen safety certifiable. There's a lot to do, and we have already made a lot of progress, especially Misra. We have an architecture that is designed for safety and can handle mixed criticality, safe, non-safe VM. We can handle real time. We can handle Virta.io and PV driver. Virta.io, we are aiming at being able to handle Virta.io between safe and unsafe VM, and also across a PCI link if you have multiple SoCs. So the idea is that you can go all the way from static partitioning simple systems such as potentially a Vision Hub type of deployment, all the way to the IVI more complex system, and multiple configuration possible. So we want to be as flexible as possible for you to be able to configure the solution that you think is best for your own architecture, your own customer, your own use case. And definitely I want to finish saying the momentum around Xen for automotive is accelerating very quickly. And just an example is Ford and Honda joining both Xen project in the last 2 months in 2 different ways. So that's the end of my presentation. So I will be very happy to take questions.
Really impressive. A lot of work done so far. Great. So a lot of applause. Are there questions from the audience? So, Ina Chai.
Yeah.
First one from Patrick, yeah?
Yeah, hello, Patrick Rufen from the German Aerospace Center. First, thank you for your presentation. I think it's a mixed view between your contributions from AMD and what's currently going on in XEN or in the overall project, right?
Yeah.
So I have two questions. On slide 9, you talked about scheduling and that you most likely want to avoid scheduling or use a null scheduler for real time. What's the current status on real-time compatible schedulers? So where you actually use a scheduler with a real-time context. Is this still ongoing work, or is this tree basically dead?
No, there are 2 real-time schedulers at the moment in the XEN tree. They have maintainers, however, they're not frequently used at the moment. Meaning that the reason is because we can do this architecture you see in the picture, and a lot of people, I didn't actually mention this. So on the same SoC, you can split your physical CPUs into 2 groups. We call them CPU pools, and you can run the null scheduler, so no scheduling, on a subset of the CPUs and a normal scheduler on the other subset of the CPUs. So what you see on the picture is actually a deployable configuration on a single SoC. So that usually takes away the need of the real-time scheduler for most people, because what they will do is they will use null for the RTOS, and they will use the normal scheduler for everything else. But as you're working in avionics, you might have very specific schedulers in mind, you know, for the 0170AC. That is still in the tree, and while it's not, you know, commonly used, it's not dead. I mean, it's working, so it's definitely possible to continue, you know, to try to use it or enhance it. Yeah.
Okay, thank you. So actually not working in the aerospace domain, but in the automotive domain. So
Okay.
we actually consider a configuration where we have few, maybe powerful cores, but we want to split a single core between multiple safety applications, maybe with 2 different partitions. So it might still be of interest for us. The other question maybe would be, you mainly, I think, talked about static configuration. So DOM0less, I think, even requires a static configuration. Does it mean there's no change possible during runtime? For example, changing CPU allocations?
No, changing CPU allocation is totally fine. That's no problem. However, so I have to distinguish what is possible with the XEN code and what we are currently considering part of the safety certification scope. In terms of XEN code, you can actually do more. You can, let me go to the DOM0 slide. You could start a system like this, and then in your DOM0 or control domain, you can even destroy the yellow domain and start another domain, or start 2 more domains. You can have a totally dynamic system, but that will not be part of the safety scope, at least that we are currently looking at. In terms of safety scope, yes, changing vCPU, scheduling, fine. But we are trying not to change the memory allocation, right? When you destroy VM and recreate VM, there is a memory allocation change. That will be out of our safety scope. XEN will support it, right? So in terms of, so if you want to try it, it will work out of the box, right? Does it make sense?
Yes. Who would control these changes if you don't have a DOM0? So if you boot DOM0less, who would be able to make these changes?
You can have a DOM0, right? So in DOM0less, the only thing it means, you don't have to have a DOM0, but you can have a DOM0. And you can even have, let me go back to the hardware domain and control domain, right? You can have both a hardware domain and a control domain, or you can even have them combined as a DOM0. So DOM0less only mean is booting in parallel, and DOM0 is not on the, is not required, is not in the middle of starting the other VMs. So you can still have it.
Okay, thank you. That helped a lot. Thank you very much.
You're welcome.
Additional questions? Everything clear, fine. So if you have questions, you can also, yeah, sorry,
Hello.
Alexandru.
Hi, thank you so much for the presentation. I have a question regarding the certification process. Maybe I understand things wrong, but isn't it also required to have design documents of your software architecture? I was wondering what tools you use to describe the design of the software.
We are using the same as before, meaning RSD files. So all the requirement as well as the architecture specification, which is already in fact going upstream, is in RSD. So we are using plain text. Drawing can be done, obviously, diagram can be drawn, and for those, yeah, this is the format pretty much also for architecture specification chapters. And individual diagrams can be like as SVG and saved in Git under SVG, for example.
Okay, I understand. And so you didn't have to essentially model the whole software architecture using UML diagrams or something like that? It was not required to do? Okay.
No.
Okay, thank you so much.
You're welcome.
Other questions? I am Niral. I hope I pronounced it correct, please.
Yeah, Ajay. Yeah, it's me. So I just wanted to know, like, is there a list of hardware which is compatible for XEN Hypervisor? Like, I believe every hardware will not be supportable, right?
So again, let me distinguish between safety and non-safety. So XEN should run on almost any hardware. So it will run on any AMD x86 platforms. It will run on our Steam competition from Intel. It will run on most ARM boards, including Renesas, for instance, NXP. In general, let me go to this slide. That I think it will make it very clear. You see, XEN actually, you see the blocks in red here, the timer, interrupt control. XEN has only few drivers. So typically, as long as XEN has a driver for one of these, it should be good. So in general, there is supposed to be a pretty wide compatibility. So let's say that you wanted to run it on a board from TI, which is not maybe officially or tested, I don't know. So it's usually just a matter of making sure there is a UART driver, you see the serial, and maybe if there is power control over firmware, like power management firmware that is specialized for this board, you might need to look at the SMC calls, but that's pretty much it. So it will work on most platforms. That said, the board that I know on top of my head that they work, aside from the x86 ones, it will work on obviously the Xilinx boards, the NXP boards, the Renesas boards, and I think there are some TI boards on which it will run, and this is just on top of my head. I'm sure there is more. Yeah.
Okay, thank you.
Chaka?
Yeah, my question is if the hardware domain, which actually shares the devices between unprivileged guests, what if the hardware domain goes down and how it impacts the system, how it serves the device sharing with the unprivileged guests?
This is a great question. So it's difficult. So let me tell you, if a DOM-mu go down, like the red one we see on the right, we can restart it, right? That's what I said already multiple times. But what if the hardware domain goes down? The problem is at the moment, we cannot restart the backends. I mean, we can restart the backend, but the connection will not establish. That is the issue. So the backend has a lot of state. Resetting the backend will cause problem to the front end. That is an issue today, right? So if the hardware domain goes down, we could restart the hardware domain, but in practice, you're not going to get back to the same functionality you had earlier because the backend will, yeah. So we have a problem there, but it's a difficult problem to solve. So at the moment, what we're trying to make sure first is that the front end can reconnect if the front end resets. But the backend being able to reconnect is a much harder problem to solve. And this is one of the cases where PV drivers are actually easier than VirtIO. So for PV driver, I would not be surprised if we could make it work with only little effort. But for VirtIO, it would be harder. Yeah.
Thank you.
You're welcome.
So there are still questions. Do you have time, Stefano? Because it's
Yeah, I can stay for a
Okay.
couple more minutes. Yeah.
Okay. So Khalif, sorry.
Hi, this is Ahmed. Thanks for the great presentation. Thanks for your patience with going over time a bit. So I had a bit interest in this specific part, freedom from interference, when it comes to multi-core memory hierarchy. And I'm curious if there is a way to learn more. So which failure modes, which interference types are considered? I know the mechanism you explained is cache coloring. Okay, I understand that. But is there a link or something to learn more later?
So I think this is one of the things that we'll need. I mean, for sure, we have documentation in cache coloring. First of all, let me start from there. And cache, I would say, is definitely the #1 source of interference, for sure, because it's just so easy to cause interference with cache. I mean, it's actually quite easy. So I would recommend to start reading the cache coloring documentation that we have in XEN. Cache coloring went fully upstream actually in the 420 release. So you can check it out. I would say that cache is #1. And after cache, then it becomes a difficult conversation, right? Because it depends on how the SoC was measuring a specific. Is how the SoC has been really the minute details of the SoCs, such as what is the bandwidth of your DDR? Is it big enough, or could one VM cause interference on the DDR, on the bus to DDR? Or what about the IOMMU? Is the IOMMU well shaped, or can it cause bottlenecks? And that is very, very board specific analysis, and very little the hypervisor can do to help. But what it can do is to give you the configuration tools so that you can do the analysis and maybe then customize the configuration and use cache coloring for the cache and other tricks to resolve the other problems. Yeah.
Mm-hmm. Yes, thank you. But I think you are on point here. So yeah, it's tricky. Multi-core and memory interference could be a very broad topic. So you have to approach it from a domain-specific perspective. And yeah, that's not going to be an easy. There is no one size fits all here. Okay. I have another question about virtual networking, especially when we talk about VMs that are deployed on the same SoC, and how do you see that from? Is this a QM topic purely, or do you see that as something that can be done in a mixed criticality deployment?
I have 3 answers for you. So first of all, it's possible to have enough Ethernet controller for everyone. Okay, this is not out of the question. For instance, on Xilinx boards, we have programmable logic. I have seen customers going in production with using, programmable logic Ethernet controller so that they will give one to each domain. And then we'll just use direct assignment. There is no VirtIO-Net or PV drivers, right? So that solved the problem. Another solution, if you have an SRIOV NIC, you can then assign SRIOV virtual functions, one to each domain, and again, problem solved. Then if we go into the VirtIO-Net front and back end, so we have the challenges that we just discussed. So at the moment, without using the extension that I mentioned, it's not really possible to have a safe VirtIO-Net front end. The back end, yes. The front end is basically impossible. But we have 2 VirtIO-Net, VirtIO extension that will publish by the end of this year that will allow you to implement a front end which is safe. So you will have to change the driver. So that's your the second way to do it. And the third way is not doing it. Meaning, if you use Argo looks like a virtual socket, like vSock is very similar. So you could use Argo between the VMs, and then one of the VM basically act like an actual network proxy. And that could also maybe solve the problem for you. So there are at least 3 ways you could tackle it for network. Yeah.
Okay, but I like that you went to the programmable logic part. So I'm a bit greedy. So, okay, is there a generic approach that you would like to include in the certified Zen for accelerators generally?
That's possible, absolutely. So we had people, this is a real example. I'm not going to share names because there is NDAs, but they went into production in medical devices. As you know, they had their own certification for medical. And I mean, what they did is having a network device in programmable logic, another network device in programmable logic. They are already part of the Xilinx portfolio and just directly assign them. And there is a programmable logic switch that you can deploy between them. So that's, from a Xen perspective, is all part of the package, right? There is nothing to be done.
Okay, other accelerators than networking are probably interesting here, but okay, just, yeah, there is a starting point. So, yeah, my last question is about real-time Linux.
Yeah.
If I have a kernel with real-time Linux kernel with real-time enabled, do you see that also deployable? And assuming this is certified for, I don't know, is it B or D? Is it deployable on top of Zen, or would it be something that uses
100%? No. We have customers using it, right? And actually, I think it's a great complement. And people often, so the thing about Linux RT is that it's good for what it is. It doesn't go down to the level of latency that Zen can guarantee, which is like 3 microseconds, right? So it's and under interference. So Linux RT will not be able to get down to those levels, and it will maybe stay up to, I've not done any recent measurements, so I wouldn't want to say, but probably around 100 microseconds or 1 milliseconds maybe. So it's a different order of magnitude, but definitely can run on Xen, and actually Xen can help by isolating away tasks that cause interference. So actually will help Linux RT be better at this job. So yeah, totally.
Okay, sounds good. Thanks a lot. And yeah, if you can share proof of concept deployment examples and requirements, a Git repo would be great. Yeah, thanks. I'm aware of the one from Elisa, the demonstrator. Thanks.
Welcome. There is one more question from Isaac.
Hey, Stefano. Thanks. Great presentation. Loved it. Yeah, Isaac from EB. I don't know if you answered this. I'm in a train, so my audio is not so great. Where would you be able to use Zen for safety? Would you be able to use it beyond AMD? Like, would you be able to get the documentation, et cetera, et cetera? Would that be possible?
Certainly, 100%. So what I mean, our goal is really to enable the community to work. I mean, if you see the names at the end of the slide, I mean, there are many companies beyond. I mean, some of us are competitors, like Renesas, that are working with us on Zen safety. I think it's the very last one. So definitely you can use Zen on other vendors' boards, and definitely our safety efforts is not only for AMD boards. Also, of course, there are certain documents that are only for AMD boards as part of our safety package. But yeah, so most of it, or a good chunk of it, will not be AMD specific.
Okay, really awesome. Thanks. Can I maybe ask one more quick question? I know we're over time.
Yeah.
Okay.
Go ahead.
The cache coloring, like you said, you map like 16 pages per VM, and so you get kind of
one every 16 page.
One every 16 pages. So you would get a lot of stage 2 mappings.
That's true.
Correct? Which
correct.
And wouldn't there be the danger of like swamping the TLB cache and maybe taking a performance hit on that, or is that not a problem?
So I think there will be a performance hit. a small performance hit, but there will be because normally you want to do the opposite, which is to put the allocation as closely together as possible, at least in consecutive 2 megabyte chunks, so that you have more TLB efficiencies. So by scattering it into 4K units, you're right, there's going to be a hit. That said, usually the people that enable cache coloring are more than happy. First of all, it's a small hit. Second, the people that enable cache coloring love to take a hit to have deterministic latency, because the negative effect of interference on latency is much higher than the TLB hit that you will get by enabling cache coloring.
Okay, got it. So you're trading off a little bit of, let's say, performance for a lot more determinism. Okay, thank you, Stefano. That's
correct. Yeah, that's correct. Well, I thank you everyone for attending and all the questions. And Mario, thank you for inviting me. I really appreciated it. And you know where to find me if you have any more questions. I am available and reachable. And you're muted, Mario.
Sorry. Okay. Yeah, thank you too for this great presentation, for your time. So I have also still some questions, but I will discuss it offline with you or another channel. Okay. So thank you everybody for joining the meeting. So we will make this video available on the Federate webpage. And yeah, let's see. Hopefully someone is joining the XEN community and contribute to that. Okay. Thank you. Bye, everybody.
Bye.
Thank you.
Thank you. Bye.
All right.